Welcome back. This is Signal Systems and Transform Chapter 6. In this chapter, we'll talk about DTFS, DTFT, and DFT. Specifically in this introduction, Chapter 6.1, we'll discuss DTFT as a transformation, different types of discrete time Fourier transform, time and frequency representation. Let's motivate first. Today, all the signals captured in the computer's digital cameras are all discrete time signals. We represent this discrete time sequence as typically x of n, where n is the time index and x of n is a value that is captured with finite precision. 16 bits or 24 bits are the typical number of bits used to represent x of n. DTFT is the Fourier transform applied on discrete sequences. dt is discrete time, ft is Fourier transform. What does DTFT allow us to do? Well, it basically breaks a signal into the frequency domain. Specifically, it breaks the signal into a sum of complex exponential. That means the sum of complex exponential can represent the signal x of n. Why is this useful? It allows us to do convolution to become multiplication in the frequency domain. It allows us to design equalizers to manipulate the signals at the various frequencies. It allows us to generate different features for classifications. And finally, in JPEG and MPEG standards, it allows us to perform compression. There are many other properties that we can use when we have converted a signal x of n into discrete time Fourier transform. You'll be able to use some of these later on. Let's examine one of the most important aspects of a linear time invariant system. Here, h of n represents the impulse response of a discrete time LTI, linear time invariant system. If we have such a system, because of the properties of linear and time invariance, given a complicated signal x of n, where we have x of n equals to this sum of three complex signals, actually when we send this complicated signal into a system, we can actually analyze them independently. This is the first signal, second signal, and third signal corresponding to these three. We can send these three signals individually to h of n, the same h of n here, and out comes the output based on the three different input. When we sum them together, this y of n and this y of n are the same. This is the interesting and most important property of linear and time invariant system. It basically says that we can break a complicated signal into its individual small little parts, see the output from these small little parts, sum them together, and it will be the same as the original signal sent to the same system. This is a statement that I have just said, which is the equivalence of the response of LTI systems to a signal is the sum of the response of the complex sinusoids, which sum is equivalent to the signal. So the question now, of course, is how do we break our complicated signal into these small parts? And Fourier transform is our answer. Fourier transform allows us to decompose any signal into infinite sum of complex exponentials. So actually when we can do that, this is what basically happened. X of n through DTFT breaks our signal x of n into sum of complex exponential. X of omega is a frequency domain representation of x of n. H of n is our discrete time system. H of n is the impulse response of the discrete time system. Remember, in our past lectures, we have showed that y of n is equals to h of n convolved with x of n. The convolution equation is actually quite expensive to calculate. Now, if you are willing to perform this operation of DTFT on x of n as well as h of n, then to calculate the output in the frequency domain, which is y of omega, all we need to do is to simply multiply h of omega with x of omega. Multiplication is very, very cheap. We can do it cheaply in the frequency domain, and then to get back into time, we simply do inverse discrete time Fourier transform. Notice that the arrow goes up here is the inverse discrete time Fourier transform. Arrow coming down is the discrete time Fourier transform. Now, if you compare this picture, this is for the discrete time domain, and on the left was continuous time. And in fact, they look very, very similar. The only difference is here is x of t representing continuous time. Here on the right hand side is x of n representing discrete time. Here the big omega representing the digital frequency. Here the continuous frequency x of m. So this is the primary motivation we have why we want to convert something into a frequency domain, because convolution is done very cheaply. The other one, of course, was, I reiterate, by breaking x of n into the complex exponentials, we can see how is the signal represented in the frequency domain. We know exactly which signals are summed to construct x of n. We know exactly which frequency has more power, less power, and its different phases. Thank you.